Okay, this is number 17 from section 7.1 of MA 259. So we're also, in this case, just going to use a table to figure out how to transform f of t equals cosine squared of 2t into a Laplace transform. And so one of the things that I wanted to point out here was this identity that we have, that the cosine squared of theta equals 1/2 of 1 plus cosine of 2 theta. So the cosine squared of 2t is equal to 1/2 1 plus cosine of 2 times 2t. So instead of theta, I have 2t. So wherever I see theta, I'm going to put a 2t. And so I see a theta, I put a 2t. And so I end up with 1/2 times 1 plus cosine of 4t. So when I'm converting cosine squared of 2t, I'm really going to convert the Laplace transform of 1/2 1 plus cosine of 4t, which makes it easier. So I factored out the half and put that out front, and then I have the Laplace transform of 1, so the Laplace transform of 1, plus the Laplace transform of cosine of 4t. And when you're flipping through your notes, we see that that's two of the properties of the Laplace transforms is I can pull constants to the outside. And why could I do that? Well, think about the integral, right? I'm setting up these integrals. I can always pull up constants outside of an integral. And then I can split the Laplace transform up across addition or subtraction. And if you think, well, why could I do that? Well, I can do that because I can split up integrals across addition and subtraction. So the properties that I can do with integrals, I can do with Laplace transforms, because remember, Laplace transforms are one special case of an integral. So I split this, I take this half and move it out front, and then I split up the 1 and the cosine of 4t into two separate Laplace transforms. So I look on my chart on page 442, and I see that 1 is 1 over s, so that's 1 over s. And I see that the cosine of 4t, I see that's the cosine of kt. So I put the k, and the k is 4. So I do plus s over s squared plus 4 squared, or 16. And so that's my Laplace transform, where s is bigger than 0.